Welcome to part 2 of our lecture this week. Let's just jump right in. Slideshow. Okay, so last time we were looking at this integral, which looked horrible. I told you could do this by integration by parts, and it's really not as bad as I made it sound last time. Let's just take a look at this. Usually when you have integration by parts, you want to make the polynomial be the u when you do this, but when you're working with a logarithm, it actually goes the other way. Okay, the reason is if you let your dv be the log, then you can't integrate to figure out what the v is. So in this case, I'm going to let u be the logarithm. Whoops, excuse me. So for this first integral, I'm going to let u just be 3. Excuse me, u is the log. I apologize, just what I said. And my dv is going to be 3 dt. And so my du will become 1 over t. And my dv will become just a 3t. And when I integrate, I'm going to have my uv minus the integral of v du. So I'm going to have 3t times log t minus the integral of, whoops, there's a dt right there, minus the integral of 3t times 1 over t dt. And these are evaluated at, my limits were 2 to 4, and this is also evaluated from 2 to 4. So you can see what happens on that. The second piece I've got to do is a separate integral because I need a different u and a different v. But again, I'm going to do the same thing. I'm going to let my u be the log of 2t and my dv be my t cubed dt. So my du becomes 1 over t. It's actually 1 over 2t times 2 for a chain rule, but those 2's cancel. And my dv is going to become a 1/4 t to the 4th. And now when I integrate, this becomes a 1/4 t to the 4th times log of 2t. Again, evaluated at my endpoints, minus the integral of 1/4 t to the 4th, another dt, times 1 over t dt from 2 to 4, and all of a sudden I have an easy integral to do. But you can see it's a lot of work. I've got 2 integration by parts to do, plus I've got logarithms in my answer, so it's pretty messy, but it could be worse. Okay, anyway, Calgon Kidnever, somebody take me away. Let's move on. In this vector, in this section of the lecture, we're going to look at a different way to calculate line integrals. However, this only works for certain cases, and that works when the vector field that you have happens to be a gradient of some other function. Okay, so here's a fact. All gradients can be written as vector fields because that's basically what they are. Remember gradients from way back. But that can't happen the other way around. So let's explore this a little bit. How do you tell? Remember, for a gradient, you start with a function, and to find the gradient of that function, you take the differential with respect to x times I plus the differential with respect to y times j. That's how you find the gradient. All right? So, to go backwards, you should be able to integrate to get back to an original function up here, but there's a quicker way to do that. Remember also, the mixed partials are equal. So if I take the partial with respect to y of this first piece and the partial with respect to x times this second piece, they will be equal if you started with this function up here. If your vector function is a gradient of some other function, then when you take these mixed partials, they'll be equal to each other. Okay? This is called a conservative vector field when this happens, and the function up here is called a potential function. So our goal is to try to find the potential function, but first we need to check to make sure that a potential function exists, and that's where we use that test. All right, so here's an example. Here's my f. Okay, so is it a vector field? If it is, then this would be f sub x of something, and this would be f sub y of something. So I'm going to take the partial with respect to y of the first one and the partial with respect to x of the second one, and let's compare and see. The partial with respect to y of this is going to be 6x plus, no y's in that, so that's a 0. The partial with respect to x of my second piece is 6x minus, no x's in that, so that's a 0. Those are equal, so yes. This is a gradient vector field. It's the gradient of some potential function. Now, if you have a gradient vector field, there's a theorem you can use called the fundamental theorem of line integrals, and it works pretty much like the fundamental theorem of calculus. And that is, if you can find an antiderivative, you can calculate the line integral without having to parametrize the function. You don't have to or the curve. You don't have to find parametric equations for the curve. You only need the endpoints of the curve. So, if you have a curve with initial and terminal endpoints, then if your f happens to be a gradient vector field, so that's what this means. If this is a gradient vector field, then you find the potential function and plug in the endpoints. No parametric equations involved. Why should we care? There's a thing called path independence. Okay, so there's one reason. So if I have a path here, and that begins here and ends here, I would get a certain answer for my line integral. But if my path looked like that, I would get the same answer. And if my path looked like this, would be easy to calculate when I have little stair steps like that, but I would have to do that as a whole bunch of separate integrals. All of those three paths will give me the same answer for the line integral. Because, I'm going to go back a slide, because the only thing that matters is the potential function and the endpoints of the path. So that's one reason why we should care. Another reason why we should care is a really nice reason, and that is if we have a closed curve. Here's a closed curve. The two endpoints are the same. So if I were to take f of my terminal endpoint minus f of my initial endpoint, those are the same number, so I would get a big fat 0. So if I know that I have a vector field for my f, I don't even have to calculate that when I have a closed path. Okay, when my path is not closed, then I've got to go ahead and calculate the endpoints. But in this case, I had no calculations needed at all because I automatically know I'm going to end up with a 0 for my integral. Okay, so here's the idea of how we're going to do it. Okay, I've got this vector field, and to check to see if it's a conservative vector field, I take these two partial derivatives. I take the f sub y here, and I take f sub x here, and I test to see if those are equal. If they are, that tells me that this little guy up on top exists. And the way that I'm going to find that is I'm going to integrate up to find this. This is my potential function. Okay. So let's look at an example. It does have a few little details we need to look at. So here's an example. Here's my f, 6xy plus 2e to the 2x times I plus 3x squared minus sine of y times j. And I think we've already calculated and found out that this was a vector field. It's a conservative vector field. We already did that in the previous example. Here's my path. I've got the top half of the unit circle. I'm oriented counterclockwise, so I'm going in that direction. So this is the point 1, 0, and this is the point -1, 0. Okay? If I were to try to do this by hand, this is horrible. Let's think about how we would do it by hand. Okay, my r would be cosine of t, sine of t, because this is a unit circle. My t would start at 0 and end at pi. And when I started to plug into my f would become 6 cosine t sine of t, which is not so bad, plus 2e raised to the 2 times cosine of t. That's all in the I direction. And then I would have a 3 cosine squared of t minus sine of t. That's going to be horrible to integrate. I don't even want to go there. So what I'm going to do is I'm going to look at this and I'm going to hope that it's conservative. Well, we know it is because we already calculated that out. We already did. So I'm not going to do it by hand. I'm going to look at the fundamental theorem of line integration. So here's what I know. I've got my f, which is an f sub x. That's my 6xy plus 2e to the 2x. And I've got my f sub y, which is my 3x squared minus sine y. I already did my test. So I want to try to find this little f up here. And the way I'm going to do it is to integrate. So I'm going to integrate each of these two functions, and they should come out to be the same thing. So I'm going to integrate my 6xy plus 2e to the 2x dx. And that should work out to be the integral of 3x squared minus sine y dy. Let's see what we get. If I integrate my 6xy with respect to x, that's a 3x squared y. And if I integrate the 2e to the 2x, that's going to become just an e to the 2x. And over here, when I integrate my second one, my 3x squared integrated with respect to y becomes a 3x squared y. My sine of y becomes a negative, so that negative turns into a positive cosine y. Now wait a minute, I told you these were supposed to be equal, right? And they don't look equal. Those two pieces are equal, so my final function has a 3x squared y in it. Here's why they don't look equal. I'm integrating with respect to x. So this is going to have a constant on the end, and that constant could have some y's in it, because remember, y is constant with respect to x. And my second piece, I'm integrating with respect to y, so that could have a constant on the end. And that constant could have some x's in it, because x is a constant with respect to y. Well, look at what, let me get some different colors here. Look at what I ended up with. Over here I have a cosine y, that's this constant. And on the second piece, I have an e to the 2x, that's this constant. So, things that only have one variable will show up on one side or the other. Things that have both variables in them, like the 3x squared y, will show up on both of those integrals. And here's my final answer. 3x squared y plus my e to the 2x, that was the constant that came from the second integral, plus my cosine y, which was the constant from the first integral. And I could have another constant that's really a number. It's a constant constant. But I don't need to worry about it because I would integrate from my endpoints and then the constant would drop out. But I do need to have those two constants with the single variables in them. Okay. So let's finish this off. I still need to finish my integration. I'm going to get rid of the parametric equations because I don't even need them. How do I find out what my points are to plug in? This is my terminal point. I'm going from 1, 0. There's my initial point. This is my terminal point, -1, 0. And so I just plug those 2 points in. So I'll have 3 times -1 squared times 0 plus e raised to the 2 times -1 plus cosine of 0. And I'll subtract off 3 times 1 squared times 0 plus e to the 2 times 1 plus cosine 0. And so I'm going to end up with, when I do my subtraction, e to the -2 minus e squared. And there's my final answer for that. Okay? No parametric equations needed. So if your path is really tough, this is a good method to use, as long as you can find the potential function. So do that test first. Or if your integrations are pretty tough, that's another good method. Okay, let's do another example. Let's evaluate 2x, 2y, so there's my f, dr, c is the upper right quarter of the circle. Oh my gosh, what does this look like? The upper right quarter of the circle of radius 3, there it is, centered at the origin, moving counterclockwise. So parametric equations for this would be 3 cosine t up to 3 sine t. It's beginning at the point 3, 0, and it's ending at the point 0, 3. Okay, it looks that doesn't look too bad. I could do this, but let's check and see if it's a gradient vector field. So I'm going to check first. So my f sub x is 2x, and if I take the partial with respect to y, I get a 0. My f sub y is 2y. If I take the partial with respect to x, I get a 0. So yes, conservative. Okay, so that means all I have to do is I integrate my 2x with respect to x. That'll be the integral of my 2y with respect to y. This piece becomes x squared plus a constant that has only y's in it. This piece becomes y squared plus a constant, should use a different letter because it's a different constant, that has only x in it. And so my final answer is x squared, which is the k of x, plus y squared, which is the c of y. And I finally just evaluate. So x squared plus y squared, evaluated from 3, 0 up to 0, 3, becomes 0 squared plus 9 minus 9 plus 0 squared. And so that becomes, in this case, a 0 for my final answer. Okay. All right. One more. 2x, 2y. Same integrand. We already know this is conservative. Because it's the same integrand as the previous slide. Look at my path. It starts here, goes around, goes over, goes up. If I were to do this by hand, I would have to do 3 pieces. I would have to do piece 1, piece 2, and piece 3, and add them all together. However, I know this is conservative, and look, it's a closed path. So, I know my answer already. Conservative vector field, closed path, the answer is 0. No calculus, well, lots of calculus involved, because we had to know all the calculus to know the answer, but no computations involved. Okay? All right, and then there's one more thing to know about conservative vector fields. A vector field, is conservative, otherwise known as path independent, if and only if every line integral on a closed path results in 0. Okay, so one way to check if a vector field is conservative is to look at every possible closed path. Okay, the other one is just to know from that test that we've done. So, looking at this example vector field, this is not conservative. Here's how I know. If I were to go around in a circle here, remember on the first lecture, we talked about how this would give us a positive result. It's non-zero. So this is not a conservative vector field. And you can see what happens when you have these little, like, they're called singularities, okay, where the vector field is going around that hole there. Okay, that's telling us that you can see is not a conservative vector field. That's it for lecture number 2. We have one more to go.